Okay, for algebra, lesson 9.2, this is part 2. This is just going to give you information on word problems, specifically using falling object model and using vertical motion model. Now, this is the one, this first part is the one that you're going to have to know for your assessment and will likely be on your EOC at the end of the year. The vertical motion model is kind of an extra. You should see it, especially if you intend to take physics. And so I'm going to do a problem like that, but the one I really need you to pay the most attention to, sorry about that, is this first page. That's the using the falling object model. This will be on your test and it will be likely seen again later this year. So it's, for example, as an object falls, its speed continues to increase. So its height above the ground decreases at a faster and faster rate. Ignoring air resistance, so you're not in physics class yet, we're ignoring the air resistance, you can model the object's height with the function h equals negative 16t squared plus c. This is the formula you will absolutely see a lot the rest of this chapter and definitely again on your EOC. Sorry, it keeps getting blurry. The height is your h, and that's measured in feet this time. The time is your t, that's going to be in seconds, and that's the object's initial height, that is c in feet. So the c term is how far off the ground it starts. For example, let's look at an acorn dropping from a tree branch. It's 20 feet above the ground. The function h equals negative 16t squared plus 20, because it's 20 feet off the ground, gives the height of the acorn after however many seconds. So that's the what we need to know is what is the graph of this quadratic function. So this one is done for you, but I wanted to take some time to explain it before we do our own, so we can find out at about what time the acorn hits the ground. So many times when we're graphing, we tell you guys go ahead and start by making a table. A lot of times this is your x and this is your y. And so this time the x is representing the t, which is the time in seconds. So at 0 seconds, it starts 20 feet above the ground. At 0.5 seconds, it's already fallen to 16 feet. At 1 second, it's increasing its speed. It's already fallen to just 4 feet above the ground. And at 1.5 seconds, when you do the math, it would be negative 16, but I like that they said this here. Do not ever plot the point negative 16 because you can't have a negative height. So this one would not be plotted. It was just to see where it hits the ground. So since 1 is still above the ground barely, but 1.5 is already negative, it's going to hit the ground sometime between 1 and 1.5, which is what our graph shows. It's just a little bit past 1. And so for that reason, it's going to have us estimate. It says at about what time does the acorn hit the ground? Well, it hits it slightly after 1 second. So then they just went and plotted this. 0.20 would be at 0 up 20. 0.516 would be at about 0.516. And then 1.4 is 1.4-ish, about right there. And so then it hits the ground just a little bit after. Okay, we have 2 U-tries, and I'm going to talk you through both of these actually. So the first U-try is another acorn problem. This time the tree branch is 70 feet above the ground. So that they give us the formula. The formula is h equals negative 16t squared plus 70. After about how many seconds does it hit the ground? Okay. So we're going to use this graph. The reason you have another graph is because it goes with this one at the bottom. So for this first U-try, we're looking at only the graph on the left. And I want you guys to go ahead and make a little mini table. Time and height. A lot of times that's your x and that's your y. That is your x-axis and your y-axis. That's the domain and that's the range. Okay, so we're going to start at 0. At 0 seconds, it started at 70 feet above the ground. So at 0 seconds, we know it's 70 feet above the ground. Actually, let's fill out our graph first so that we make sure that we have these labeled. So if the y-axis is the height, and it needs to go up to 70, let's count by tens. So 10, 20, 30, 40, 50, 60, 70, that's where we start. And again, that is the height, so let's label that. And the height is in feet. Okay, this is the seconds. We could do 0.5, 1 second, 1.5, 2 seconds, 2.5, and this is the time in seconds. Okay, so at 0 seconds, we start at 70 feet. Okay, let's find out where we are at 0.5 seconds. So at 0.5 seconds, that's our t time, so we're going to plug in 0.5 for t. So remember, you have to do order of operations. So we're going to square it first, and then multiply by -16. So we're going to do 0.5 squared times -16. Okay, and then we have to add the 70 where we started from, so plus 70. And that is 66. So it has dropped to 66 feet after half a second. Let's see where it's at after 1 second. So 1 squared is 1. 1 times -16 is -16 plus 70. So -16 plus 70 is 54. So now it's down to 54 feet. Okay, let's keep going. 1.5 seconds. So 1.5 squared times -16 equals -36, but we've got our plus starting height, which is 70, so plus 70. It's down to 34. So it's really picking up speed. This is where gravity comes in. And that's why the formula, by the way, is always -16. It's not like I'm picking that. That's the standard formula for an object falling. Okay, and then let's try 2. 2 squared is 4. 4 times -16 plus 70 is 6. Okay, so we're getting very close to hitting the ground. We're now only 6 feet above the ground. So let's go to 2.5. I think that's going to be too much, but let's try. 2.5 squared times -16, yeah, plus 70. You're already at -30. And remember, we're not graphing negative heights because that's not possible. So 2.5 seconds is too long. So, I mean, we could try like 2.1 seconds maybe just to see. So at 2.1, if we square it, times -16, yeah, that's really close, plus 70, you're at just barely past where it hit the ground. You're at -0.56. So we still wouldn't graph that, but it's not at 2, it's just right after 2. It's between 2 and 2.1 seconds. So let's graph the rest of these though. So at 0.5, it was 66. So 66. At 1 second, it was 54 feet above the ground. At 1.5, it was 34. At 2, it was 6. And then at 2.1, it had already passed. So let's go ahead and make just basically the rest of this graph. And it's just going to hit at barely just past 2 seconds. So I like that it says at about. What time does the acorn hit the ground? So I'm going to use my squiggly equals because that means about. I'm going to call it at about 2 seconds. We could say like just over, but just over 2 seconds, about 2 seconds is fine. Again, we're estimating this. I think in your Math Excel, it's going to ask you something about the range. Obviously, it's not going to ask us about the domain because the domain is a little bit too hard to predict. It's between 0 and a little bit more than 2, but that's hard to say. But the range we know for sure. The range goes from 70 where it starts and then it hits the ground at 0. It never goes negative. So if it asks you for the range, you could put that it's between 0. So y is your range, is between 0 and 70 feet. So the range is somewhere between, it's greater than or equal to 0 always, and it's less than or equal to 70 always. So the y goes in between 0 and 70 feet if it asks you for the range. Okay, this next question, I'm going to do it a little bit differently. It's a physics class demonstration. A ball is dropped from the roof 72 feet above the ground. So this is the formula, h equals -16t squared plus 72 because that's where it started above the ground. And graph the function and determine how far the ball has fallen from 0 to 1 second. So at 0 seconds, where is it at, and how far has it fallen between 0 and 1 second? So let me make sure I keep this stuff straight. So this stuff was all that problem, and now we're looking at the second graph for this bottom one. So I was going to move it, but actually let's just do it right here. So t for time, that's your x value. H for height, that's your y. Let's go ahead and write your axes in and pick your scale. I think let's go by tens again since we're starting at 72 up the y-axis. So 10, 20, 30, 40, 50, 60, 70. I'm going to go ahead and put 80 on there just because we start at 72. And we know then at 0 seconds, it's starting at 72. Okay, and this is once again height in feet. And across the bottom, we can do once again 0. Let's do 0.5, 1, 1.5, 2, 2.5. I don't think we'll probably need more than that because 72 is very similar to 70, so it's probably going to be between 2 and 2.5 again. And remember, this is time in seconds. Okay, so our 0.5, remember, you always have to square it first. You have to do order of operations, then multiply by -16, and then go back and add 72. So 0.5 squared times -16 plus 72, where we started, 68. Okay, after 1 second, let's see how far it's fallen. 1 squared is 1, times -16 is just -16. So we just need -16 plus 72. 56. Okay, at 1.5 seconds, 1.5 squared times -16, and then we need to add that 72, is 36. All right, let's see where we're at 2 seconds. 2 squared is 4 times -16, and then we add that 72. We're getting really close to the ground. We're 8 feet above the ground at 2 seconds. So again, I think 2.5 is going to be way too many. We can double check. 2.5 squared times -16. Oh yeah, plus 72. We are -28. So we're not going to graph that one because you can't be negative past the ground. We can try a 2.1 again just to kind of see if that's about where it's at. 2.1 squared times -16. Yeah, that's very, very close. Plus 72. We're still above the ground, but barely. 1.44. So we could actually graph that. It would just be very close to hitting the ground at 2.1 seconds. So at 0.5, we're at 68. So 0.5, we're still at 68. At 1, we're at 56. At 1.5 seconds, we're at 36. At 2 seconds, we're 8 feet above the ground. Took a drastic drop there. And then at 2.1 seconds, you're basically right there at the ground. So let's draw in your arch and see about where it hits the ground. So again, it's going to say about, actually this question is different. It says graph it, which we did. And then it says determine how far the ball has fallen between the time of 0 seconds and 1 second. So we're looking at how far it has fallen from 0 seconds to 1 second. So it has gone from 72 feet above ground to 56 feet above ground. So if we subtract those two, 56 from 72, it has fallen 16 feet. So this answer is it has fallen 16 feet. Okay, the second page I want to do a little bit differently with you, but I do want you to know one quick thing. Anytime you have a problem like this, which is what we've been doing this whole time, I'm just going to make one up. I'm just going to say, what if it was h equals -16t squared plus, I'm going to say that the height was 64. Just to make it easy, let me just give you an extra problem. This is not part of this down here. So if we were doing this problem and it didn't give you graph paper, you could absolutely go ahead and solve this just algebraically, just mathematically. And the reason is because the height, we need it to be at 0. It can't be a negative height. We need to know when something's going to hit the ground. So if we make our height 0 and we write this equation, you can actually just use math and you're solving equations to solve it. So you would subtract 64. You would subtract 64. Okay, I've definitely run out of room, but I'm going to move this to the other side. You'd have negative 64 equals negative 16t squared. And the next step you would do if you were solving this equation is you would divide both sides by negative 16. You would be left with t squared equals, I believe that's 4. And you would square root both sides because t squared equals 4 means that t would have to be equal to 2. So I know this one worked out nice and neat because I picked a number that I knew was going to come out to end it perfectly. But if it didn't give you graph paper, you could always just set your h equal to 0 and solve it to see how many seconds. Remember, t represents time. So how many seconds it would take something to hit the ground if it started 64 feet above the ground. So you can always make your height 0 because that's what we're trying to find out is when the object reaches the ground, when it's at 0 feet. So this would be another way to do it if you don't have graph paper. Okay, for the vertical motion model, this is kind of above and beyond. I really want you guys to see this, but I'm not going to spend a lot of time working it out because it is not going to be assessed until Algebra 2. So I'm going to just show you how to use your Desmos calculator and plug something like this in. So what they're saying is during a halftime of a basketball game, a slingshot, these people are holding a slingshot, they're launching t-shirts into the crowd. It has an upward velocity of 72, blah, 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 blah. None of this matters until you come down to see what the function is. So here's the function. H equals negative 16t squared plus 72t plus 5. So I'm going to go to my Desmos calculator, and you can just search Desmos graphing calculator. And remember, I am going to type in a y and an x instead of h and t because your Desmos calculator works with x's and y's. So I'm going to put y equals negative 16x squared plus 72x plus 5. Okay, so y equals negative 16x. I have to pull up this calculator squared. Okay, and then plus 72x. You can see that it's already popping up there, plus 5. Okay, so what I want you to see is, and I know it's a graph that goes on forever, I'm going to zoom out a little bit so we can see the height. So it started 5 feet above the ground at 0.5. They launched it. This t-shirt launched up into the air. It hit its maximum point at about 2.25 seconds. That's the x-axis, 2.25. And its height is the y-coordinate. That's 86 feet before it started falling again. And then it would have hit the ground. If it didn't go into the crowd, it would have hit the ground at a little over 4.5 seconds. So if we come back to our paper to look, they showed that the height of its height was 86. And we actually found that just by using our Desmos graphing calculator. We knew it was going to go 86 feet. So it's really important that you guys know how to work the Desmos calculator. We know that the range is between 5 feet to 86 feet because it launched from someone who was 5 feet tall, not necessarily, but it launched from, they pulled it back a little bit. And so it started at 5 feet and it reached its maximum height at 86 feet. So that would be the range from 5 to 86. Okay. Method 1, they actually worked it all out, and you could do this, but I'm not going to spend time doing that today on an extra problem anyway. Method 2 was use a graphing calculator, which is what I wanted you to see. We don't need to do the you try. If you want to, great, do it, but it's another t-shirt problem. I'm going to move on to this baseball thrown into the air. The formula for the baseball is negative 16t squared plus 30t plus 6. That means whoever threw it was probably 6 feet tall, throwing it from their height. So how long will it take the ball to reach its maximum height, and what is the ball's maximum height? And then what is the range? So again, I'm going to use my Desmos calculator, and I'm going to leave all of this the same, except I'm going to change the middle number to 30, the B term to 30, and then the C term to 6. So The b term this time is going to be 30. The c term this time is going to be 6. So I can zoom in a little bit to see this one more. Remember, we're ignoring all of the negative values because it's not possible in this type of situation. So the person started at 6 feet tall throwing it. So they threw the ball straight up. It hit its maximum height at, this is why Desmos is good, because look at those numbers. They're terrible. At about 0.9 seconds. So that's not even one whole second. And its maximum height was just over 20. So we're going to call that about 1 second and about 20 feet high. So if we go back, we're going to say its maximum height was about 20 feet, and it says how long, it took it about 1 second. So if it wants to know the range, remember the range again is the y value. It started at 6 and went all the way up to a little over 20. So we're going to say that it was from 6, the ball was a little over 20, but we'll call it about 20. So this would be the range of the function.